Now see, we already discussed this thing. When any charge q is moving in the magnetic field, the force acts on it. So we can understand this thing. If any current carrying conductor is placed in the magnetic field, then it will experience the force, because after all, in the current carrying conductor, the charges are in motion. So when any current carrying conductor is placed in the magnetic field, it implies that the moving charges are in the magnetic field. Now here, suppose as shown in the figure, we have uniform magnetic field in which a conductor having length L is placed. Which one is connected with the battery? Now when the circuit is switched on, suppose current I is flowing through this particular conductor in the direction as shown in the figure. And now we have to derive the equation for the force acting on this current carrying conductor. Clear?
Yes, sir.
Now, suppose here the number density of charge carriers in this conductor, that is small n. Number density means the number of charge carriers per unit volume, that is equal to n. Now here length of the conductor is L and its cross-sectional area, that is suppose A. Then the total volume of the conductor, that we can write A into L. Now per unit volume, the number of charge carriers, that is N. Therefore, in total volume AL, the number of charge carriers will be how much? So we can write, therefore, the total number of charge carriers in the given conductor, that is NaL. Okay. Now, if here in the conductor I current is constituted due to flow of those charges, and here the charges are moving with drift velocity. So we can write the magnetic force on total q amount of charge which are moving with velocity Vd, which are constituting the current I in the conductor. That is q into Vd cross B. Now, this total q amount of charge, that is how much? So we already calculated the total number of charge carriers in the conductor. So total number of charge carriers, that is NaL, and these charge carriers are electrons. So per charge carrier, the charge is E. So total amount of charge flowing through any cross section of the conductor, that is NaLe, which one is constituting the current I in the conductor. So replace Q by NaLe. Okay. Now we have the equation J, that is the current density, equal to NeVd. So we can replace this NeVd by current density J. So we can write the equation for the magnetic force, that is equal to A L J cross B. Okay. But A into J, that is current I, because current density J, that is equal to I upon A. So we can replace this A into J by I. So we can write the magnetic force, that is IL cross B. Here IL, or suppose in some cases we consider infinitesimal small line element of the conductor. Then we can write IDL. So this product of I and L or IDL, that is called current element. That is called current element. And here, when we consider the current element, at that time we have to take care about this thing. We have to consider the line element or the length of the conductor that is perfectly parallel to the direction of the flow of current. Okay, so here see, you can observe one thing. When this A and J, A into J, that is replaced by I is the scalar quantity. At that time, the vector sign that is placed on L, because the direction in which the current is flowing, in that particular direction we define the current density. And when we take the current element in the direction of the flow of current, it implies that L and J both are in the same direction. So when L and J both are in the same direction, then in that case, if you place the sign of the vector on J or L, it represents the same thing. Clear? So here now resultantly we can say this thing: when any conductor having length L carrying current I is placed in the magnetic field B, the force acts on it, that is IL cross B. And the direction of this force, that is perpendicular to both IL and B, and the direction of this resultant force that can be fixed with the help of right-handed screw rule. Clear? Now, if the current carrying conductor is not the straight one, suppose the current carrying conductor that is as shown in the figure. Now this particular conductor or the wire is carrying current I. So in this particular case, what we have to do? We have to divide this particular conductor, or in other words, we can say the entire length of the conductor into so many infinitesimal small line elements. And when we consider infinitesimal small line element, then we can prepare the current elements as IDL1, IDL2, IDL3, IDL4 up to IDLn. Why we divide this one into so many infinitesimal small line elements? Because when we prepare the current element, at that time, we have to take current and the line element both parallel to each other. And for this type of curved conductor, we have to take infinitesimal small line elements. Now, here, suppose the line elements are DL1, DL2, DL3 up to DLn. Corresponding to it, we prepare the current elements IDL1, IDL2, IDL3 up to IDLn. Now, the forces on these current elements that we can write F1, that is equal to IDL1 cross B, that is the force on the first current element. F2, that is IDL2 cross B, that is the force on the second current element, up to Fn, that is equal to IDLN cross B, that is the force on nth element. So in this way, first of all, we have to calculate the force acting on each and every current element, and then after take the vector summation of all these, we will get the resultant force acting on that current carrying conductor. So we can write the resultant force F, that is equal to sigma I equal to 1 to n I dl I cross B. And this summation that we can represent by integration also. Here I, that is constant throughout the conductor. So we can write resultant force F, that is equal to I integration dl cross B, and this integration should be carried out over this line of the conductor. Clear to all of you?